Okay, now we're moving on to our next speaker, and that's going to be Mina Dogucu, who is an assistant professor in the Department of Statistics at the University of California, Irvine. Her book, Bayes' Rules, which, by the way, is an absolutely brilliant title, is also widely praised. So Mina's going to talk to us and tell us a little bit about what's going on with undergraduate Bayesian education in the United States. So over to you, Mina.
All right, so greetings from Los Angeles, and it's the morning where I fail at everything. I hope I can get this straight. I hope that's full screen.
Yes, it is.
Perfect. So I think some of the point I also wanted to talk a little bit about why we should be teaching Bayesian methods, but I think Mark has covered pretty much all the points here, so I'll skip this part quite fast. One reason is p-values and that famous quote by George Cobb that he posted on American Statistical Association forum. Why do so many colleges and grad schools teach p equals to 0.05? Because that's still what the scientific community and journal editors use. And why do so many people still use p equals to 0.05? It's because we teach it in schools. And I think this is just not showing the issue with use of p-values, but it's also a reminder of how much scientific practice and teaching are intertwined. So if you're talking about Bayesian methods, it's use of Bayesian methods in science is almost an absolute must that we have to teach it. There's also, like, in terms of, to add to the numbers that Mark has shared, perhaps from the United States, for us, like American Statistical Association's journal has applications and case studies articles. And this is the statistics that was reported by Jeff Whitmer in the latest JSM meeting. And in 1985, about 10% of these articles used Bayesian methods. And in 22 and plus half of 2023, because JSM is in August, that amount was 49%. So it's evident that in practice, Bayesian methods have definitely picked up more. And in terms of teaching, I think one thing is definitely the intuitive aspect of it. Teaching of Bayesian methods, when we think about p-values, many people still interpret it as probability of hypothesis, even after multiple statistics classes. And same with confidence intervals. They are very hard to teach because there's only one sample, one confidence interval, but then we have to make students imagine 100 confidence intervals from 100 samples. So as opposed to these credible intervals, really give that relief to students of being able to say there's a 95% probability, the thing they actually want to say. And it's also important to teach Bayesian methods in addition to frequentists, just because it gives that complete picture of philosophical aspects of doing science, like what is it to know, what's to do, hypothesis testing. So having students know both perspectives is also important. And also considering that it is more widely used these days, Bayesian methods, it's also our duty to prepare them for their future career as well. And one of the best parts of it is teaching Bayesian methods is actually teaching statistics and computing in one class at the same time, and having like computing examples that are very meaningful. And I'll give an example towards the end. This is especially important with emergence of data science and computing being even more relevant than before in statistics. So there are a few examples we had in the literature that were focused on teaching Bayesian statistics at the undergraduate level, including Jeff Whitmer's class at Oberlin, and Jingchan Moniko, who is another person who teaches Bayesian methods, and Andrew Hogue also teaches Bayesian methods. And we also, Jingchan Moniko Hu and I also talked about our classes as well. So what we had in the literature was like few examples of classes from different universities, but we also wanted to know what is going on at the national level, if possible, in undergraduate Bayesian education. So we did a study, and this is already published in the American Statistician. So during this talk, I will give few summary findings of the study and the methods. And hopefully it will also answer some of the previously asked questions, especially I think the question that Syria had asked to Mark previously. So our aim was this: we wanted to know how commonly Bayesian statistics taught at the undergraduate level, and we also wanted to know how it's taught. But obviously this is a very big aim, especially at the national level. Of course, our study has many limitations, but I'll talk about some of the methods we've done. So we collected data on all universities with a ranking of 100 or higher, and also from liberal arts with a ranking of 50 or higher. So for anybody who's not familiar with liberal arts colleges in the US, we have liberal arts colleges that are basically specifically undergraduate institutions. They are less likely to have PhD programs or something. And we searched the word Bayesian in their course catalogs, spanning 2 academic years from fall 2019 to summer 2021. We thought 2 years was a good timeline because we know that US bachelor's degrees are 4 years, and there needs to be some preparation for a student for the Bayesian class. So if a course is offered every 2 years, then probably students would be able to take it if they wanted to. And when I say course, I'm referring to module, excuse my language. And we only track courses that contain the word Bayesian in the title, just because if it was in the course description, it would be very hard to judge if a course is Bayesian enough or not. So we are looking at courses that have the Bayesian in the title. We looked at whether which departments offers these courses, whether the courses are cross-listed between undergraduate and graduate enrollment. For more advanced courses, there are sometimes classes where undergraduate and graduate learners are in the same class. And we also wanted to know whether it's part of any major, whether it's an elective or a required course, and major in this case is the degree program. And we also track the prerequisite, and I think this will give shed some light to the questions already asked. We also try to collect syllabi of these courses and try to track course content. So results, here we go. So among 152 high-ranking institutions, we've identified only 46 institutions that offer a Bayesian course. So majority don't offer Bayesian courses. And we have in 46 institutions, there were 51 Bayesian courses. So that means 5 of the universities had 2 Bayesian courses, not a single one. And we also looked at by institution type, 12% of the colleges had it. So it's less commonly encountered in liberal arts colleges, and 39 of the universities had it. And of the 45 courses that we have found, 60% were cross-listed between undergraduate and graduate programs, which means many of the undergraduate learners are actually learning Bayesian methods along with their graduate peers. So looking into the departments, 51% of the courses were offered in statistics department, 7.8 was offered in computer science departments, 2% was offered in math. And there were also many departments that were at the intersection of, like, it could be like math and statistics department, or a computer science and math department, or a data science department. So it's like stats and data science. So if it's a combination of any of these two, any of these 4, so in such departments, 17.6% of the Bayesian courses were offered in these departments. And we also found, which was, I think, one of the most interesting findings of our research, was 21.6% of the courses were taught in departments such as physics, psychology, ecology, evaluation, and marine biology, and so forth. And I will soon show majors as well. This was very inspiring to see, because this also showed like necessity of Bayesian methods training in other scientific fields that's beyond statistics departments. And this led to one of our research, one of our grants that was funded by National Science Foundation. So our idea was we need to train students in all fields, especially STEM fields, in Bayesian methods. So looking at majors, statistical sciences, these courses were part of statistical science majors, math majors, and the combination of math, computer science, or data science majors. And as I mentioned, there are also some programs like in biological science, quantitative econ, psychology, public policy, and so forth. They also have some Bayesian courses. But what was interesting is when we look at elective versus required comparison, for most students, Bayesian methods is an elective course. And there are very few institutions that require Bayesian methods, but looking at it's very few, perhaps it's very difficult to make generalizations from this, but I think it's still interesting to see that 2 of the 4 required courses were part of a stats major, and 2 of the required courses were part of data science major. And hard to interpret, but one of the reasons is because major changes are difficult, and perhaps adoption of Bayesian methods as a requirement in majors might be difficult, but data science majors are relatively newer. So that's probably why like 2 already have Bayesian methods as opposed to stats majors that we've had for many, many years, and only 2 of them have, only 2 have these courses. And speaking of prerequisites, so Bayesian courses have a lot of prerequisites. And I should perhaps mention that we're not just counting prerequisite of the Bayesian course, but we're also counting prerequisites of prerequisites as well. So the question is, how many courses does a student have to take before they can even get into the Bayesian course? And so the median number was 6. And one thing that's worth noting is if you're talking about actually making Bayesian methods be more common for other STEM students, such as psychology, astronomy, physics, and so forth, it's probably these students are not necessarily going to take 6 statistics courses and then take a Bayesian course. So we have to definitely think about our ways of reducing the number of prerequisites and making it more accessible. So in terms of prerequisite types, 43 of the 51 Bayesian courses had 3 calculus courses as prerequisites, and 29% also required 2 calculus courses, and 10% required 1 calculus course. So this is also varying whether students are just going with single variable calculus versus multivariable calculus going into Bayesian courses. And there were also courses that did not require calculus at all. And we also looked at linear algebra. 37% did require linear algebra going into Bayesian courses. And in terms of computing was a little bit harder to track because they were not necessarily very consistent across institutions as calculus would be over centuries of training. So 33% of the courses mentioned some sort of computing prerequisite, but these are not necessarily a course prerequisite. So they could be something like specifically courses like introductory computer programming or R for data science with R, or it could be SAS programming. But some of them also just mention some software in their course description, like we recommend R knowledge, familiarity with R, basics of R programming required. But at least the consistent trend is there is some computing requirements in 33% of these courses, at least mentioned explicitly. And going on to probability and statistics requirements, most required course was probability, and then linear models, probability and statistics, and mathematical statistics. And there were, of course, some Bayesian courses, like some institutions that had other Bayesian courses. So 2 of these Bayesian courses had the previous Bayesian course as a prerequisite as well. And looking over the content of these courses, actually, these were, this is like the sample, part of sample syllabus that we have come up with. And the paper actually has a short term, like 10-week term sample syllabus and 14-week term sample syllabus, if anybody is interested looking at. But overall, I think the themes were foundation of Bayesian inference, where there is some conjugate models like beta binomial, normal, and then focus on conjugacy and then prediction. And then there is some Middle part of the course that's like focused on Bayesian computing, that could be MCMC, Gibbs sampler, Metropolis Hastings, and then MCMC diagnostics. And then courses move on to Bayesian modeling, such as linear regression, hierarchical, GLM, and logistics. And we've also tracked books. People see, so there are quite a lot of options in books, and there are numerous numbers, not certain books, of course, shine, like BDA, doing Bayesian data analysis, and now a first course in Bayesian statistical methods. But there are numerous books that others use. So based on these, we had few recommendations to make. We should definitely expand the access to Bayesian courses. We can offer an undergraduate in Bayesian statistics if we can, and definitely reducing the number of prerequisites would expand that access, especially to students who will not necessarily be taking 6 stats courses in their undergraduate career. And another option is including Bayesian modules as part of existing courses, or I should say, including Bayesian units as part of existing modules. And making Bayesian courses a part of majors is also important, as we've seen most students were taking these electives. So perhaps making these required as part of majors could be one step. And also, if they are electives, we've seen in some institutions, they have recommended electives, highly recommended electives. So making Bayesian methods shine from different electives could be another step for students to choose that. And also making this elective just beyond our own stats students would also be very meaningful. Making these accessible to other STEM students would make the field more accessible for others. And balancing statistics with computing is also important. This includes simulation-based learning early in the course. We've seen this in other people's syllabi, and this seems to be the norm. And encouraging students to write self-coded MCMC algorithms. This also seems quite common. And this can be done with single parameter or multi-parameter models. And this really helps them learn. And I'll give an example for this. And if the course puts equal emphasis on computing and modeling, then perhaps using one of the probabilistic programming languages for MCMC would be great. And we also teach, some of us teach, where actually emphasis is stronger on modeling rather than computing. So students do not necessarily have the time to learn languages like Stan or JAGS. So in those cases, for those of us who are teaching with R at least, there are wrapper packages for STEM. For instance, our STEM ARM, BRMS. So the focus can shift to understanding statistics rather than actually being able to write the syntax. And I will provide few examples from our Bayes rules just to give some ideas of like that emergence of computing and understanding from pedagogical perspective. One is definitely use of visuals. I guess after Ben's animations, these visuals won't do any justice. But actually visualizations definitely help with that intuition building of the relationship between prior and likelihood and how they impact posterior. So for instance, in this figure, we see different sample sizes and how posterior is impacted by the change in sample size and how likelihood, first of all, is impacted versus how different priors are shown in rows, but this intuition can be supported, intuition building can be supported with visualizations. And I had mentioned writing MCMC algorithms. So for instance, in Bayes rules book, we do cover Metropolis Hastings. I'm not going to go through the details of the algorithms. Actually, I have a previous talk on TALMO, I think, recording, where I talk more about what we do with Bayes rules. But I think this is very important of that actually teaching statistics and computing at the same time is when we teach functions in computing topics, we usually use actually silly examples, like just to show functions. But here, students are able to actually write a function that they will use for real. And in order to write this computing aspect of this code, they also have to understand the relationship between prior and likelihood and how that actually impacts the posterior. And also, in order to write this code, the student really has to understand Metropolis Hastings algorithm as well. And once they can write that code, they are also able to visualize once again. And this is much better because they wrote the code themselves. They know what each iteration is. Trace plots become a little bit more meaningful because they have written the code themselves. And I will finish off by sharing a few resources for those who might be interested. We do have a website with some undergraduate Bayesian education resources that includes textbooks, papers written on this topic. We also have a Slack for undergraduate Bayesian education network. If anybody is interested, feel free to email me to join. And I wanted to share my Stats 115 course materials that are open source and open access. And I did mention making Bayesian methods accessible for STEM students. So one of our projects has been training STEM instructors in Bayesian methods for them to be able to teach their own students. So this project is called BaseBats. And we do have resources for that project as well. Like the professors who are teaching to their own students, they have developed materials for them to be taught to their own students. And some of this work was supported by National Science Foundation, so I wanted to thank them for funding us. They made the research that I talked about open access, and thanks to them, the second grant that I've listed here, that's the BaseBats, thanks to them, we actually get to talk about Bayesian methods and try to spread the education of Bayesian methods to STEM instructors. Thank you.
Thank you very much, Mina. So can I just remind everyone, if you've got questions, please put them in the Q&A function rather than the chat function on Zoom. So we already have one for you, Mina. So this is the issue of people being quite resistant to changing. So you showed quite dismal results as to how much Bayesian stats is actually taught. So do you have any ideas of sort of, I think the poster here said sort of carrots for trying to get people to give more Bayesian type courses?
Yeah, so I think this change is very difficult. And one thing I also started trying to teach Bayesian in my introductory level courses, actually, as a challenge to see if you can give up that 6-course barrier. And I think, at least in the United States, I can say that our introductory statistics courses with more recent years, like decades, should I say, have shifted from being calculus focused to non-calculus focused. And I thought that's some inspiration we can get in terms of making Bayesian methods accessible as well. Because I think many of us think about teaching the way we learned it. Like many of us learn Bayesian methods after having taken 6 statistics courses, perhaps, or even some of us complete degrees and then learn Bayesian methods later on. So I think we should, when it comes to education, we have to think not about how we learn, but how the new generation will learn. I think making each other aware that, like now, these days, we teach normal distribution, and do students necessarily know PDF of normal distribution before they actually start learning about hypothesis testing from frequentist perspective? Not necessarily. They don't even not necessarily normal's PDF, but any PDF. So I think that switch can happen for Bayesian. That is also possible. Like we have this paper, like we try to teach K-12 teachers Bayesian reasoning and incorporation of prior ideas. So I think it's a very difficult, like that change is very difficult. But I think some things we can do is advocacy, like being more vocal about it. Second thing is trying to develop resources that are more accessible. Like, because all of us learn Bayesian methods at a higher level, we should actually try to produce teaching methods that are at much, much, much lower level. And there are people actually, like one person is Sibel Kazak, I can type the name later. She like works with kids like very young kids, subjective probability reasoning. So like we can talk about probability reasoning even in K-12, like it's not like a very, very advanced topic. Of course, we can always know more. I'm not saying Bayesian methods is like a baby job, but we need to make it more accessible.
Thank you, Mina. And just maybe one final question. We've had a couple of questions which are very similar in terms of getting students to actually write their own code. So are you worried in any way that somehow that this could lead to students perhaps getting it a bit wrong, and therefore, you know, their understanding of it isn't going to be quite right?
Mm-hmm. So I think in this case, like writing code, at least the way I do it is like support them. Like in the book too, we actually walk through the code. I think one way of doing it is like, for instance, in my class this year, I just finished the Bayesian course actually. I teach gamma Poisson, like I support them in writing Metropolis Hastings for gamma Poisson model, and then they have to write it for beta binomial. And in beta binomial, the parameter is bound by between 0 and 1. Almost like 25% of my students get it wrong. And it's okay being wrong. Like we should never be scared of students being wrong. And they will eventually find it because they will get trace plots and they will see things not looking as they should. So I think it's okay to let students being wrong as long as we are monitoring them.
Thank you. There is another question for you in the chat, but I think in the interest of time, we'll move on and perhaps you can answer that question directly.
Good.